Hello everyone, welcome to Gatewala. So guys, Gatewala has already started GATE Aerospace preparation, and all of you, those who are in the final year or the third year or second year, you guys can start your preparation with Gatewala. Here, all the faculties who are going to teach you are one of the best faculties in India for teaching all the subjects, and all the faculties are highly qualified. So today we are going to discuss on a very important cycle which we use in aircrafts or aircraft propulsion and all the fighter jets that you see. So this cycle is basically called as Brayton cycle, and it is used in gas turbines. Okay, so today is the second lecture for propulsion series, and guys, I'm going to teach you all aircraft propulsion, jet propulsion, and everything related to aerospace propulsion. Guys, my name is Vinod Kumar Datusliya. I am All India Rank 1 in GATE Mechanical. I have done my MTech from IIC Bangalore in Aerospace Engineering. Then after that, I have worked for around 6 years in General Electric. I have designed one of the most efficient aircraft engines. You might have heard the name of LEAP, G9X. So these are the engines on which I have worked. I have designed extensively. I have designed aircraft engines, and I'm also teaching at Gatewala. So guys, let's today let's start this interesting topic, which is the gas turbine, which is the practical working cycle for all the thrust generation or power generation in case of fighter jets or aircraft. So before going for the gas turbine cycle, gas turbines actually work on a cycle which is called as Brayton cycle. Okay, so you might have heard about Brayton cycle, but all of you, those who have not heard, let me give you a very brief background on how this cycle has come up. So before starting the Brayton cycle, first let's understand how this cycle has come from. So I'm sure you might have heard that in thermodynamics, there is one very basic cycle which guides all the thermodynamic cycle. And that was designed by what is called as the father of thermodynamics, which is Carnot. So you might have heard about a cycle that is called as Carnot cycle. Okay, we will study extensively about this cycle in the full course in detail. But I am sure those of you who have studied something in aerospace, you guys might have seen how does a Carnot cycle actually looks like. So if we plot a Carnot cycle on a TS diagram, TS diagram is the diagram on which most of the cycles are actually drawn. Okay, so if you see, we have a Carnot cycle that moves something like this. Okay, so if we talk about the TS diagram, the Carnot cycle consists of four processes. There are four processes. Okay, so the first process is called as, let's say we go from 1 to 2. Okay, so first process is called as isentropic compression. So if you see over here, the entropy remains constant, and there is an increase in temperature. This process 1 to 2 is called as isentropic compression. Okay, so this is governed by a law of thermodynamics, which is written as PV to the power gamma equal to constant. So now those of you who are studying this lecture for the first time, probably you might not be aware that what is PV to the power gamma equal to constant, or how does this vary? Because if you have not studied the basic thermodynamics, then probably it will be slightly difficult for you to understand, because this is what is basic thermodynamics. Basic thermodynamics will be taught by Shivam sir, and I'm sure most of you might have studied basic thermodynamics in your college, so you might be aware that what does a isentropic compression process actually looks like. Okay, moving on, the second process, which goes from 2 to 3, this is called as constant temperature heat addition. So 2 to 3 process is isothermal It is called as isothermal heat addition. Heat addition. So now if you see the term, first term is isothermal. That means the temperature is constant. Iso, that means same, thermal means temperature. So the temperature remains constant. So if you see T2 and T3, this is a horizontal line. So at every point, the temperature is constant. So in this process, isothermal heat addition, temperature is constant. Okay? And you see the heat is being added. So in this cycle, heat added from external source, which we called as, let's say, heat supply. Okay, so this is what is heat being supplied. Then the next process from 3 to 4, if you see 3 to 4, which comes downward. So you see this is opposite of 1 to 2. 1 to 2 process was isentropic compression, where we increase the pressure and the temperature of the working fluid. Similar way, 3 to 4 is called as isentropic expansion. So 3 to 4 is isentropic expansion. Now, can anybody tell me if this isentropic expansion is happening, which law it will be following? So can I say isentropic expansion will also be following PV to the power gamma equal to constant? Any isentropic process, compression or expansion, both will follow PV to the power gamma equal to constant. So that is very interesting process. As we study the detailed course, we will see this. The next, going for 4 to 1. So process 4 to 1. Now tell me, when we are coming back from 4 to 1, what will happen? So while you were going on the right hand side, this was an isothermal process and heat was getting added. If we reverse the process, that means we are coming this side. When the entropy is getting reduced, the temperature remains constant. This is called as isothermal. It is called as isothermal heat rejection. Is it clear? Isothermal heat rejection. Again, this temperature is constant. So guys, this is the most basic cycle, which is the Carnot cycle. This is the ideal cycle, and everybody compares the whatever the cycle, thermodynamic cycles are there, everybody compares those cycle with this cycle. Why do we compare with this cycle? Because this is the most efficient cycle. So when we will study the details of this, we will see that none of the cycle can have efficiency better than this. This is the cycle which is the most efficient cycle. Okay. But this cycle is not practically possible. We cannot design this cycle for practical applications because the process 2 to 3 and 4 to 1, these are isothermal process. And we will see that isothermal processes are extremely slow processes when compared for gases. These processes, isothermal heat addition and isothermal heat rejection processes, for gases, they are extremely slow. That means they take lot of time. When you have to transfer heat from 2 to 3, you will see that it will take a lot of time. So when it takes a lot of time, can you wait for that heat transfer to happen? No. We want our cycles to be very fast. We want our cycles to generate a lot of power. And that can happen if the cycle is moving very fast, so that, let's say, in 1 second, you have 1000 cycles running or 500 cycles running or 100 cycles running. So you will produce a lot of power. Okay. So to move this cycle, we have to be very fast, but this process is extremely slow. Similarly, this process is also extremely slow. So there are two processes, both of which are extremely slow. So can we use these processes in normal working? No. The answer is simply no. That becomes very difficult to run it. So then how do we design our cycles? How do we run our cycles? So running of those cycles was actually, or practical designing of those cycles was actually implemented by some of the scientists. And one of the cycle which was actually designed by a scientist called as Ericsson. There was a guy whose name is Ericsson. So that guy actually designed a practical working cycle for some instrument, and that cycle became what is called as a Brayton cycle. Okay, so we will see how does a Brayton cycle actually look like. But to understand how he actually got to Brayton cycle, first I'll tell you how he actually got the Brayton cycle. So you know that Brayton cycle, this process is not possible. Okay, so when this process is not possible, let's say I remove this. Okay, I am removing this. I will draw another rectangular box so that you get an idea of how he designed it. So this is your Carnot cycle. Let's say 1, 2, 3, 4. This is your 1, 2, and 3, and 4. So you know that the process 2 to 3 and 4 to 1, they are extremely slow process. You cannot run these processes. So you cannot use these processes in your cycle. Very good. Can we use these two processes 1, 2, and 3, 4? Yes, we can use them. So there was a person whose name was Ericsson. Okay, his name is Ericsson. Okay, so Ericsson designed two cycles. He designed cycle 1 and then he designed cycle 2 also. Okay, so Ericsson 1 cycle we will not study, but we will study the Ericsson 2 cycle, which is the practical working cycle for gas turbine. So what he did is, since a cycle has to transfer heat, and heat transfer at constant temperature is not possible. So when you want to transfer the heat, how come the heat be transferred? Okay, so how can the heat be transferred? So heat transfer can happen through three processes. First process is temperature equal to constant. Second process is equal to pressure equal to constant. Third process is volume equal to constant. So there are three processes by which heat transfer can happen. So you know that first process we cannot use because this is extremely slow. We cannot use. Can we use pressure equal to constant process? Yes. So how do we do this? How do we move this process which is called as pressure equal to constant? So this is achieved by a device which is called as heat exchanger. So we have a device where the process will move at constant pressure and there can be extremely fast heat transfer. This is what is actually happening in the real life nowadays. Okay, so we will study this. Can heat transfer happen at volume equal to constant? Yes, that is also possible. So people have designed this process also. This is also possible, and this happens in Otto cycle. Otto cycle, which is practical working cycle for IC engines. When we will study this, we will see that this is also an extremely fast process. So this is a fast process, this is a fast process. Both the processes can be used for heat transfer. Okay, so let's say if you have to use the first process, pressure equal to constant. So how does a pressure equal to constant line look on this cycle? So if I say the pressure equal to constant line looks something like this. So this is pressure equal to constant. This is a line. Okay, so can I do the heat transfer at this line? Can there be a heat transfer happening at this point, this pressure equal to constant curve? Yes, there will be heat transfer. So this heat transfer we can get achieved, or we can achieve this in a device which is called as heat exchanger. So you can supply heat over here, Q supply. Okay, so now you have made two processes. This is, let's say, location 1. This is location 2. I will mark this as 2 dash. So 1 to 2 isentropic compression process can move. 2 to 3, instead of doing a heat transfer at isothermal or temperature equal to constant, you can transfer the heat at constant pressure. So that happens at constant pressure. Now you move from 3 to 4, where actually heat, actually work output happens, or isentropic expansion happens. And then 4 to 1. Again, you have to remove this. So you have to have heat transfer either at pressure equal to constant or volume equal to constant. So Ericsson used again the same process, which is pressure equal to constant. So he used the fourth process, which is pressure equal to constant. So now you see you have a cycle that can actually run Okay, and this cycle was called as Ericsson 2 cycle. This cycle 1, 2, 3, 4, which is called as Ericsson 2 cycle. Okay, this cycle name is Ericsson 2 cycle. But guys, there are a lot of people who claim to have designed this cycle. So this phase is, when this cycle was designed, the phase is in Europe, starting of 18th century or 1800, or starting of 19th century, 1820. So in that era, when you see, everybody was engaged in designing the cycles. So this cycle is claimed by 3 scientists. This cycle is called as Ericsson 2 cycle. Joule also claimed that he designed this cycle. So this cycle is also called as Joule cycle. And there is a person that is called as Brayton. He also said that I designed this cycle first. So this cycle is also called as Ericsson 2 cycle, or it is called as Joule cycle, and it is called as Brayton cycle. Okay, and this cycle was used in gas turbine first in 1905 to propel an aircraft. Okay, this was first gas turbine was actually used, or first gas turbine actually propelled or powered the first aircraft in 1905. It was a test flight. Okay, and after that, this engine revolutionized everything, or this cycle revolutionized everything. So now let's see how does a Brayton cycle actually looks like. So when we talk about the ideal Brayton cycle consists of 4 processes. It consists of 4 processes. So 1 to 2 is called as isentropic compression. 1 to 2 is isentropic compression. This process is governed by PV to the power gamma equal to constant. Then second process is 2 to 3. This says, or this tells about the heat supply. So we have heat supply happening, and this is pressure equal to constant. Pressure is pressure equal to constant. Okay? So this second process is pressure equal to constant. Then the third process is happening over here, 3 to 4, where actually the power is generated. Okay? And this happens in isentropic expansion, which is PV to the power gamma equal to constant. And again, the fourth process, which is 4 to 1, is again pressure equal to constant. And here, heat rejection happens. Okay? So if you see over here, there are 4 processes. These 4 processes happen in 4 devices. Okay? So the first process happens in 1 to 2. That is called as compressor. Device where 1 to 2 happens is called as compressor. And you will see when we will do the analysis, we will see that there has to be a work provided to compress air. So this is called as work of compressor. There has to be work provided. We compress the air. So the working fluid in this cycle is gas. It is used for gas as the working fluid. So gas over here is at low pressure, low temperature. That gas is compressed. So when that gas is compressed, it attains high temperature, high pressure, and volume is reduced. So when the temperature is increased, when the pressure is increased, you have to compress it. You have to provide the energy to gas to compress it. Okay. So once the compression happens, then the gas is sitting at high pressure. Now you provide energy from outside. You provide heat energy. So we supply, this is heat energy which is provided. Okay. So when heat energy is provided, you see the temperature of gas increases from 2 to 3. So the temperature over here is this, and then it increases over here. Okay. So now you have a high pressure, high temperature gas sitting at location 3. Now we use that gas in turbine to do certain work. So when you use that gas, you see there will be some work which is generated by turbine. So we have certain work WT. And once that work is done, now the gas has expanded to a lower pressure. It has again come at lower pressure and a lower temperature. And after that, as per the second law of thermodynamics, any cycle which is running on thermodynamic heat, it has to reject heat also. 100% of the heat cannot be converted into work. So when you have supplied heat, there has been some work done. You have to reject some heat also. So you reject the heat. So from 4 to 1, we go in heat rejection. That happens at constant pressure again. Okay, so this is how your cycle actually moves. There are 4 processes and there are 4 energy interaction: work in compression, heat supply, work in turbine, and heat rejection. Okay, so these are the 4 processes. Now let's see how does these processes actually move in a gas turbine. So we have 4 components over here. So you see the cycle is run by 4 devices. First device is called as the compressor, where the air or gas enters at location 1 and comes out at location 2. Once this gas comes out at location 2, now that gas is heated up at constant pressure. So when the gas is heated up, the heat exchange happens at constant pressure. So let's say we have gas entering over here. So I am drawing a heat exchanger over here. Okay, so this is a heat exchanger, and again you will see that there will be another heat exchanger over here where the heat exchange happens. So you see the energy transfer happens from high temperature source. This is high temperature source where high temperature gas might be coming in and it will be transferring heat to air, and then air moves out. So there are different ways of heat addition which happens over here. Okay, so heat is added over here. So you supply the heat add, okay, happens over here. Then you move at location 3, which is entry to turbine. And now turbine does the work. In the turbine, the expansion of gas happens. And when expansion of gas happens, some work is delivered or it is developed by turbine. Once that work is done, now the low temperature, low pressure gases come over here. Okay, and those are cooled back. So again, the heat rejection happens. So heat is rejected. Okay, and again, the cycle completes. You come back at location 1. And this cycle repeats multiple times. Okay, so once the cycle repeats, now you can see that this cycle will continuously work. So when this cycle is running, we will see, when we will do the analysis, we will see that the work required in compressor is very high. Generally, what happens is, if a turbine is developing 100 joules of work, the work required to run the compressor is of the order of 40 to 50 joules. That means 40 to 50% of the work which is developed by turbine is actually consumed by compressor. So in practical gas turbines, what we do is we club this turbine with compressor, so that when this turbine is running, when this turbine is rotating, it will transfer the work to compressor. So there is a work which is developed by turbine. So turbine develops work WT, okay, and this work, part of that work is transferred to compressor. So you have the net work which is developed by turbine, or net work which is developed by cycle, is work of turbine minus work of compressor. What is work of turbine? You see, the work of turbine is the work which is extracted over here. So this is work of turbine, this is work of compressor. So part of that work is again fed back over here. So the W net will be lesser than work of turbine. I hope everybody has understood this. Yes, it is absolutely clear to everyone. I am sure you must be aware of it. So how this cycle is used in gas turbine, we will see it later when we will be doing extensive analysis. At that time, I will tell you how the different components of compressor looks like, what are the different stages, how does the blades look like, how does the heat exchange happen over here, how does the turbine run, what are the different stages in turbine. Okay, so we will see everything. But before seeing, or before going for actual cycle, let's do the analysis of cycle. Okay, so when we do analysis of cycle, we will go back to this cycle. We will do the analysis of all the 4 processes. What are the heat interaction happening? What are the works developed? What are the temperatures? What are the pressures that we will see in the cycle? Okay, so the first thing that we are going to see is the pressure. So in the Brayton cycle, you will see that there are two pressures which we actually see. So let's say at location 1, we have pressure is 1 bar. The atmospheric air is sucked in, okay, or let's say air you have fed into the system which is at 1 bar. Now when you put it under compressor, can I say the work of compressor is to increase the pressure? So compressor increases the pressure of gas to, let's say this has become 10 bar. Okay. So at the inlet the pressure is 1 bar, at the exit the pressure is 10 bar. Now you see heat exchange happens. So when heat exchange happens, what happens? The process is constant pressure. So you see the pressure remains constant. So the pressure at exit of the heat exchanger is also 10 bar. Okay. So at the exit of compressor is 10 bar, at the exit of heat exchanger is also 10 bar, or at the entry of turbine is 10 bar. Now this gases go inside a turbine and they expands over there, and let's say the pressure is again reduced to 1 bar. Okay. And now this 1 bar exhaust gases are coming inside the heat exchanger. Again the process is happening is constant pressure. So now you see that there are two pressures which actually divides your cycle. There are two pressures. So one pressure is, let's say, in the upward portion. So starting from here till the turbine inlet, there is a pressure which is everywhere 10 bar, and there is a pressure in the bottom part which is 1 bar. So you see there are two pressures over here in the cycle. This pressure which is present in the top portion is called as the high pressure, and the pressure which is present in the lower portion is called as the low pressure. So we define, when we do the analysis of the cycle, we define a pressure ratio. For this cycle, this ratio is one of the important parameter. So we define a pressure ratio that is written as R, and that is equal to P2 by P1, or it can also be written as P high by P low. Okay. This is one of the most important parameter for Brayton cycle. Okay, we are going to see why it is very important. Okay, but I hope everybody understood what is pressure ratio. That is P2 by P1, which is also equal to P high by P low. Okay, very good. Next, we are going to see that isentropic compression, when the process PV to the power gamma moves, PV to the power gamma equal to constant, when this process moves, there are three relations which are associated with this law, PV to the power gamma equal to constant. Okay, so when a process is moving from, let's say, 1 to 2, when the process is moving, the first equation that you can use is P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Okay, PV to the power gamma equal to constant means P1 V1 to the power gamma equal to P2 V2 power gamma. Okay. Similarly, when this relation is converted in the terms of temperature and volume, this can become TV to the power gamma minus 1. T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. This is the second relation that we use. Okay. And the third relation that we use is in terms of pressure. So, T P to the power gamma minus 1 over gamma, or 1 minus gamma over gamma. Okay, 1 minus gamma over gamma. T1 P1 is equal to T2 P2 1 minus gamma over gamma. Okay, this relation can be written in a much better form. T2 by T1 can be written as P2 by P1 to the power gamma minus 1 over gamma. It is nothing but rearranging these two terms. Okay, so you will put T1 over here, you will put P2 over here, and you will reverse the sign gamma minus 1 over gamma. So it will be P2 by P1 gamma minus 1 over gamma. So this is in the Brayton cycle, this is one of the most important relation, because this is what we are going to use most of the time. Okay, so this relation we are going to use. Then in the analysis of Brayton cycle, we will require one more equation which is called as the conservation of energy, and that equation is actually called as steady flow energy equation. I'm sure in thermodynamics you guys might have come across this equation, or in the last lecture, in the first lecture also I had told you what does this equation looks like. Okay, in the last lecture of nozzles we have already seen how does a steady flow energy equation look like. So let's say you have a device. In this device, let's say there is a fluid which is entering. This equation is applicable to the flow devices, okay, where the fluid flows from one location to another location. So let's say there is a fluid which is entering the device at location 1. With itself it is carrying enthalpy, with itself it is carrying kinetic energy, with itself it is carrying potential energy. Okay, now there is certain heat which is added. So let's say you have some heat added Q dash, and there is some work W out which is done by this device. Okay, and there is energy which is going out. So enthalpy going out, kinetic energy which is going out, and potential energy which is going out. So yesterday or in the last class we had seen that these terms can be combined together to have conservation of energy. So in steady state we can combine all these terms, and you see this equation can be written in a much better form. Okay, so using steady flow energy equation says H1 plus V1 square by 2 plus ZZ1 plus Q dot will be equal to H2 plus V2 square by 2 plus ZZ2 plus W out. So on the left hand side we have all the energies which are coming inside this device. So H1 V1 square by 2 ZZ1 and Q dot. And on the right hand side we have energy which is going out, H2 V2 square by 2 ZZ2 plus W out. Okay, in case of thermodynamic cycle, so generally we have, it is not always necessary. So generally we have velocity 1 is almost equal to velocity 2 and Z1 almost equal to Z2. This is applicable for generally for cycles only. Okay, when we are going to study the jet propulsion, at that time this will not be applicable, because in jet propulsion we will see that V1 and V2 will be very different. Okay, so if you use these two, then your equation can be written as H1 plus Q dot is equal to H2 plus W out. This is what is your simple equation looks like. Okay, this we had seen in the last lecture also. Okay, so today we are going to utilize this equation as well, and we are going to do the analysis of the 4 devices that we have. Okay, so when we talk about the first device, which is the compressor. So compressor is the device where isentropic compression happens. What do you mean by isentropic compression? When we talk about the term isentropic, isentropic means entropy remains constant, and this process has Q dot is equal to 0 and your PV to the power gamma equal to constant. Isentropic is reversible adiabatic. The process is reversible adiabatic. So when you have adiabatic process, when Q dot is 0, so can I say I have to insulate this device such that there is no heat transfer happening over here? So there will be no heat transfer happening. There will be only one interaction happening, and that will be the work which is provided to the compressor, okay, which is coming from the turbine. So if I have to use steady flow energy equation over here, can I say the energy which is coming in? So H1 plus V1 square by 2 plus ZZ1 plus work of compressor. This is the energy which is coming in, H1 V1 square by 2 ZZ1 from here, and work of compression from here. So that is the total energy coming in. And what will be the energy going out? Energy going out will be from there. So it is H2 plus V2 square by 2 plus ZZ2. Okay, and we know that simply using V1 is almost equal to V2 and Z1 almost equal to Z2. Can I say H1 plus work of compressor is equal to H2? And from here you can write work which is required to be given to compressor is H2 minus H1. work which is required to be given to compressor is H2 minus H1. And since there is a gas which is moving from here, so there is a gas which enters at this location. The gas enters at location with temperature T1. Let's say gas is coming out at temperature T2. So for gases, we know that for gases, enthalpy is a function of temperature only. I hope everybody knows that. So if you don't know, don't worry. We are going to teach you in thermodynamics, basic thermodynamics, that enthalpy is a function of temperature only. So if enthalpy is a function of temperature only, then we can write work of compressor is equal to H2 minus H1. And the joining relation is H2 is equal to Cp into T2 minus H1 is Cp into T1. Okay. So from here you can write work of compressor will be equal to Cp into T2 minus T1. This is the work which is required in the compressor. And this work, the unit of this work will come out to be kilojoule per kg. Okay. So the work required per kg would be kilojoule. ठीक है, Cp T2 minus T1. In case we are given a mass flow rate, if m dot kg per second mass flow happens, ठीक है, if this happens through the turbine, then the work required in compressor will be equal to m dot multiplied by Cp into T2 minus T1 kilojoule per second, or it can be written as kilowatt. Okay, so work required in compressor will be equal to m dot Cp T2 minus T1 kilowatt. I'm sure everybody has got it. This is very, very, very basic, very fundamental relation. I hope everybody has got it. It's clear to everyone? Yes. Okay. Now let's go to the second device, which is called as heat exchanger. So now what is happening in the heat exchanger of a gas turbine? You see that there is a gas which is entering over here at location 2. There will be a gas which is going out. The same gas would be going out at location 3. But there will be certain heat supply. So you will be given with Q supply. Okay. So heat supply. So heat supply is happening. So can I use steady flow energy equation over here? So using steady flow energy equation, can I write H2 plus V2 square by 2 plus ZZ2 plus Q dot supply. ठीक है, that will be equal to H3 plus V3 square by 2 plus ZZ3. Okay. And if we assume, we again assume that V2 is almost equal to V3 and Z2 is almost equal to Z3. ठीक है? Then these two terms, V2 ZZ2, V3 ZZ3 will go out, and you see that H2 plus Q dot supply will be equal to H3. And from here you can write Q supply. In fact, you should remove the dot from here, because dot is generally used for per second. So we can simply write Q supply. So that will be equal to Q supply, that will be equal to H3 minus H2. Okay. And again, we know that H3 and H2 will be functions of temperature. So Q supply can be written as H3 minus H2, which is equal to Cp T3 minus T2. So Q supply will be equal to Cp T3 minus T2, and the unit of this will be again kilojoule per kg. Okay. So unit of Cp is kilojoule per kg, Kelvin, multiplied by the temperature difference is Kelvin. So the unit will be kilojoule per kg. Okay. So this is the heat that you supply per kg. And again, if there is a mass flow rate m dot, if m dot is the mass flow of the fluid through the cycle, then the net heat supply Q dot can be written as m dot into Cp into T3 minus T2. This we write as small because it is per kg basis. Then we have Q dot. This is for the complete mass flow. And the unit will be kilojoule per second or kilowatt. Okay. So the net heat supplied in the heat exchanger is m dot into Cp into T3 minus T2. I hope it is clear. I hope it is clear. Okay. So now let's go to the third device that is called as the turbine. Okay. So again, in turbine, we have seen that the process that is followed in turbine is isentropic expansion. So when you say isentropic expansion, we have seen isentropic means Q will be 0, Q supply or Q reject will be 0. Okay. There will be process followed will be PV to the power gamma equal to constant. So you see when Q supply or rejected is 0, this is adiabatic. So there is no heat transfer happening. There is only one thing happening over here, that is expansion of gas, and which will generate the work WT. So work is developed by turbine. So again, we can use steady flow energy equation over here. And you see steady flow energy equation would write H3 plus V3 square by 2 plus ZZ3. This is the energy which is coming in, and there are two energies which are going out. One is work and other is location 4. Okay? So this would be equal to H4 plus V4 square by 2 plus ZZ4 plus work of turbine. Okay? Again, we will assume that V3 is equal to V4 and Z3 is equal to Z4. V3 is almost equal to V4 and Z3 equal to Z4. This will lead to these two terms will go away, these two terms will go away. So H3 will be equal to H4 plus work of turbine. And you see now we can write work of turbine from here. So work of turbine will be equal to H3 minus H4. This can be written as Cp into T3 minus T4. So work of turbine, work developed by turbine is Cp T3 minus T4. And you see this work will be kilojoule per kg of the gas movement. Okay. And if m dot is the mass flow, if it is the mass flow of gas or air, then we can see that the net power developed by turbine, work developed by turbine will be equal to m dot into Cp into T3 minus T4, and this will be kilojoule per second or kilowatt. Okay. So this is very simple as that. Okay. Now let's go to the last device, which is the heat exchanger, where the heat rejection happens. So now you have a low pressure, high temperature air which is ready to transfer the heat, or it is ready to throw the heat to atmosphere. Generally the heat is rejected to atmosphere. So you have Q rejection over here. Okay. And if heat rejection happens, there is no work that is developed in the heat exchanger. So if you want to write the steady flow energy equation, we can write H4 plus V4 square by 2 plus ZZ4 will be equal to H1 plus V1 square by 2 plus ZZ1 plus Q rejection. Okay. So the energy that is coming in is H4, V4, Z4. And that is going out is H1, V1, Z1 plus Q rejection. Again, V1, V4, these terms will cancel. Okay. ZZ1, ZZ4 will be equal. V4, V1 will be equal. And you will be left with only 3 terms. And from here you can see that heat rejection will be equal to H4 minus H1. And this can be written as Cp T4 minus T1. So heat rejection will be C4 T1 minus T4 minus T1, and the unit will be kilojoule per kg. Okay. So the heat rejected by cycle is Cp T4 minus T1, and if mass flow rate is m dot, then heat rejection will be equal to m dot into Cp into T4 minus T1, and the unit for this is kilojoule per second. I hope everybody has understood how we have calculated what is the heat supplied, heat rejected, work in compressor and work in turbine. All the four processes are clear. I am sure everybody must have understood it. Now you see that there are two more relation, or in fact three more things that we need to see over here. So the first thing that we are going to see is in the compressor. So in the compressor, we have seen that work required in compressor is Cp T2 minus T1. But how do we calculate T2? This T2 that you are seeing over here, generally in Brayton cycle, what happens is he will provide you T1. If T1 is known, or if T1 is given, how do we calculate T2? Because work in compressor is Cp T2 minus T1. So you should know what is T2. So to calculate T2, we use the relation PV to the power gamma equal to constant. That means T2 by T1 is P2 by P1 ki power gamma minus 1 over gamma. And what is P2 by P1? I am sure everybody has now understood that this is compression pressure ratio, not compression ratio, pressure ratio. So R to the power gamma minus 1 over gamma. So across the compressor, you have the temperature relation. T2 minus T1, or T2 by T1 is R to the power gamma minus 1 over gamma. So from here you can calculate T2. T2 will be equal to T1 R ki power gamma minus 1 over gamma. So once you have calculated T2, if he has given you temperature T1, he has given you pressure ratio, then you can simply calculate what is the temperature T2. Okay? Similarly, across the turbine, when we are writing the turbine, we say the work required in turbine is Cp T3 minus T4. So generally what happens is they provide you temperature T3. T3 is generally given. It is generally fixed. This T3 is generally fixed based on what is the material capabilities. How much temperature can a material sustain? And the best materials that we have can sustain up to around 1500 degrees centigrades. Okay, so these are generally the temperatures. Slightly lower than that would be the temperature at the entry of the gas turbine. So once T3 is given, how do we calculate T4? Because that will give us what is the work which is developed in turbine. So again, T3 by T4 can simply be written as P3 by P4 ki power gamma minus 1 over gamma. How? Because the process followed is isentropic compression, isentropic expansion. So if isentropic expansion happens, T3 by T4 is P3 by P4 ki power gamma minus 1 over gamma. And you know that P3 is equal to P2 and P4 is equal to P1. So P2 by P1 ki power gamma minus 1 over gamma, and that simply is equal to R to the power gamma minus 1 over gamma. So you see the temperature ratio across turbine also is R to the power gamma minus 1 over gamma, and this we have earlier calculated that this will also be equal to T2 by T1. So in case of a gas turbine, in case of Brayton cycle, there is a very interesting relation that comes, and that is T3 by T4, that is temperature ratio across turbine, is equal to T2 by T1, which is the temperature ratio across compressor, is equal to R to the power gamma minus 1 over gamma. This is one of the most powerful, it is one of the most powerful relation, okay, that we see. So from here, you can see that T3 is written as, or T4 is written as T3 divided by R ki power gamma minus 1 over gamma, and T2 is written as T1 R ki power gamma minus 1 over gamma. Is it clear? Okay, I hope everybody understood. Okay, So now once you have calculated these temperatures, now we are going to see what are the relations of W net and efficiency. So if we want to calculate what is W net, can we say the net work developed by cycle will be work by turbine minus work of compressor? And what is the work developed in turbine? It is Cp into T3 minus T4 minus Cp into T2 minus T1. So this will be the work developed in cycle, that is kilojoule per kg. Okay. And when you have to develop the relation for efficiency, what is efficiency? Efficiency of Brayton cycle can be defined as W net divided by heat supply. W net divided by heat supply. Can we write it like this? Okay. And you see, W net divided by heat supply can also be written as, so for a cycle, we know that from first law of thermodynamics, from first law of thermodynamics, what does the first law of thermodynamics say? I hope everybody must have studied the first law of thermodynamics. First law of thermodynamics is conservation of energy, okay, which says delta Q is equal to delta U plus delta W. That means if there is a system, to this system you provide certain energy. If you provide certain energy, then that system will do few things. So it will do certain work, delta W, and it will store some of the energy. So whatever is the energy that you are supplying, it will store certain energy and it will do certain work. That means if 100 joules of energy is supplied to this system, what it might do is it will do 40 joules of work, and remaining 60 joule, it will increase its own internal energy. So delta Q is equal to delta U plus delta W. This is what is the first law of thermodynamics. It talks about one process. Okay. Let's say the same rule applies to the 4 processes that we are seeing. 1, 2, 3, 4. Isentropic compression, heat added, isentropic expansion, heat rejection. When these 4 processes happen, your cycle would move from one location and it will come at last location over here. So 1, 2, 3, 4, and again back to 1. So if your system has again come back, like it has moved from one location 1 and it has come at location 1, can you say that the properties of all the properties of the system at location 1 will be same before starting the cycle and after coming from the cycle? So can I say delta U net should be 0? If your system has started from one location and again it has come to the same location, that means temperature, entropy, everything will be same. And if everything is same, if temperature is same, then the amount of internal energy it is carrying will be same. So delta U net will be 0. So let's say if I have multiple cycles or multiple processes. So for a cycle, first law of thermodynamics, if I put it in the form of summation, if there are multiple cycles or if there are multiple processes happening, then the first law of thermodynamics can be written as delta Q. Summation of delta Q will be equal to summation of delta U plus summation of delta W. Okay. And if this is put for cycle, so for cycle summation will be 0. So you see that net resultant delta Q will be equal to net resultant delta W. That means Q net will be equal to W net. Q net will be equal to W net. This relation is called as the first law of thermodynamics for a cycle. So the net heat transfer to the system will be equal to the net work done by the system. Okay. So let's say if I want to write the W net of Brayton cycle. Can I write W net of the Brayton cycle is work of turbine minus work of compressor? Should this be equal to Q net? And what is Q net? What will be Q net? You see that Q net will be equal to Q supply minus Q rejection. Q net, that is the net heat supplied to the system, is Q supply minus Q rejection. Okay. Why we are writing this? We are writing this because efficiency, when you write W net divided by heat supply, this can also be written as W net can also be written as Q supply minus Q rejection divided by Q supply. And when you write this, you see that efficiency can be written as 1 minus heat rejection divided by heat supply. And now you can put the formulas for heat rejection and heat supply in this equation to calculate the efficiency of Brayton cycle. Okay. So efficiency will be equal to 1 minus heat supply is Cp into, so if we write for per kg basis, it is T4 minus T1 divided by Cp into T2 minus T1. Okay. So it can be written like this: 1 minus Cp into T4 minus T1 divided by T2 minus T1. Okay. So now you see that we can rearrange this formula. So you see Cp will cancel out. Okay. And this relation will be equal to 1 minus T4 minus T1 divided by T2 minus T1. Okay. This is very interesting result. Okay. So now what we will do is we will reframe this. So I will write 1 minus, I will take T1 common from the top. This will become T4 by T1. Sorry. Heat supply, I have mistakenly I have written T2 minus T1. It is T3 minus T2. Okay. So T3 minus T2. Okay. So I will take T1 common from the top. This will become T4 by T1 minus 1. And I will take T2 common from the denominator. So it will become T3 by T2 minus 1. Okay. So 1 minus, on the numerator it is T1, T4 by T1 minus 1. And denominator T2, T3 by T2 minus 1. Now let's see this relation once again. The last relation which I have shown you over here, T3 by T4 is equal to T2 by T1. So let's see this relation once again. T3 by T4 is equal to T2 by T1. Okay. So what happens if I exchange these two terms? I take T4 over here and I bring T2 down over here. Can I write this relation will become T3 by T2 will be equal to T4 by T1? Can I write like this? See, this is very interesting. T3 by T2 is equal to T4 by T1, because the same thing you will use over here. So T3 by T2 is equal to T4 by T1. So T3 by T2 minus 1 and T4 by T1 minus 1. Will these two terms become equal? Okay, so this and this you can cancel out. And once you have cancelled those out, you will be left with one of the remarkable result. Efficiency of Brayton cycle is 1 minus T1 by T2. Very easy relation. 1 minus T1 by T2, or this can also be written as 1 minus 1 over T2 by T1. And what is T2 by T1? T2 by T1, you know that 1 minus 1 over R ki power gamma minus 1 over gamma. Okay. And this is the efficiency of Brayton cycle. You will see that this efficiency depends only on two terms. Efficiency depends only on, so the first term is most important, is R, which is the pressure ratio. It is the pressure ratio. And the second term on which it depends is gamma. Okay, which is dependent on what is the material of, or what is the nature of gas. Monoatomic gas, diatomic gas, triatomic gas. So gamma is ratio of specific heat. It is 1.67 for monoatomic gases. It is 1.4 for diatomic gases, and it is 1.334, let's say, triatomic. Okay. So generally we use this Brayton cycle, which is used in aircrafts, is mostly used with air. So for air, we have gamma is 1.4 because air is diatomic gas, which consists of nitrogen and oxygen. Both are diatomic, and it constitutes 99% of both these gases. Okay. So for air, we have efficiency is 1 minus 1 over r to the power gamma, which is 1.4 minus 1 divided by 1.4. Very interesting result. Okay. So this is all about the Brayton cycle. This is the theoretical Brayton cycle that we are studying over here. Now we are going to do certain, we will do two questions over here, and then we will see how the efficiencies are calculated in case of a Brayton cycle, and how it impacts the temperatures, or it impacts the energy that is taken out from the cycle. So let's say question 1 says air enters a compressor of a Brayton cycle at 1 bar and 300 K. If the pressure ratio is 6, find the efficiency of cycle. So it is given that pressure P1 is 1 bar, temperature T1 is 300 Kelvin, and he says the pressure ratio, which is R, which is P2 by P1, that is equal to 6. He is saying find the efficiency of cycle. So efficiency of cycle, we have already seen that it depends only on one parameter. So efficiency is 1 minus 1 over r ki power gamma minus 1 over gamma. Okay. So you see that he has already given you air. Air enters the compressor. So for air, gamma is 1.4. So 6 to the power 1.4 minus 1 divided by 1.4. Okay. So now you will put these values in calculator, and it will be 1 minus 1 divided by 6 to the power 1.4, 0.4 divided by 1.4 will be equal to 5 divided by 3. Okay. So this will become 1 minus 3 divided by 5, which is equal to 0.4. So efficiency of this cycle is 40%. This efficiency is very low. This efficiency is very low. Why this efficiency is low? To understand why the efficiency is low for this cycle, let's take few examples. So we have already seen that the temperature T1 is 300 Kelvin and pressure ratio is 6. Let's take one temperature T3 is 1500 Kelvin. The temperature at which air enters the gas turbine is 1500 K. So let's draw this cycle, and then I'll tell you why the efficiency of this Brayton cycle is extremely low. The efficiency is low because when you see the cycle is running, this is location 1, location 2, location 3, and location 4. So we have already seen temperature T1. Can we calculate temperature T2? Yes. We can calculate T2, that is T1 into R ki power gamma minus 1 over gamma, that is 300 into 6 ki power 0.4 divided by 1.4. When you will see, when you draw this, it will be equal to 500 Kelvin. So temperature T2 is 500 Kelvin. So from here we can calculate what is the work required in compressor. So work required in compressor is Cp into T2 minus T1, that is 500 minus 300, that is equal to 200 Cp. So the work required in compressor is 200 Cp. Now let's go to the turbine. So we have already seen the temperature T3. Temperature T3 is 1500 Kelvin. So I will write these temperatures over here so that you will better understand the scale. 300K, 500K. This is 1500K. Okay. Now let's calculate T4. So what will be T4? T4 will be equal to T3 divided by R की power gamma minus 1 or gamma. So T4 will be equal to 1500 divided by 6 की power 0.4 divided by 1.4. Okay, when you do this, it will be T4 will be equal to 1500 divided by 5 by 3. So T4 will be equal to 900. And can we calculate the work of turbine? So work of turbine will be equal to Cp into 1500 minus 900, that is 600 Cp. Okay, so work of turbine is 600 Cp. So the work developed by turbine is 600 Cp and work consumed by compressor is 200 Cp. What will be the W net? W net will be equal to 400 Cp. CPU values you can put 1.005. So you'll get kilojoule per kg. Okay. But let's understand that this is the work. But let's understand what is the heat supplied. What is the heat supplied that is happening and what is the heat rejection? How much is the heat supply and how much is the rejection? This is 900 Kelvin. So to understand heat supply is Cp into T3 minus T2. And this will be Cp into 1500 minus 500, that is 1000 Cp. And what is heat rejected? Heat rejected is Cp T4 minus T1, that is Cp 900 minus 300, that is 600 Cp. So you are supplying 1000 Cp. Q supply is 1000 Cp. Q rejection is 600 Cp. And W net is your 400 Cp. You see, the efficiency is very low because the heat that is getting rejected is extremely high. You have to reject the heat at large amount. And that happens because the gases which are coming out of here, they are extremely hot, 900 Kelvin. And these gases you are directly discharging energy to atmosphere. This is extremely high temperature. The Brayton cycle is very inefficient because the expansion gases which has expanded after the turbine, they are still at extremely high temperatures. These gases have enormous amount of energy which you are not able to utilize it. And that is why this cycle has very low efficiency. If somehow we can harness this energy, then our efficiency can be improved. Okay. So we will see how this energy can be harnessed. But let's do one more question over here regarding to simple Brayton cycle. So this question you guys should try. Air enters the compressor of Brayton cycle at 1 bar and 300 K. If the pressure ratio is 6, find the mass flow rate of air required to produce 1400 kilowatt power if the maximum temperature in the cycle is 1200 Kelvin. Cp is given as 1.0. I hope you guys can attempt this question. You guys can attempt this question. Okay, so you guys can pause the video and then you can attempt this question. So in the meantime, I will draw the temperatures. I will draw the cycle. Most of the things we have already calculated over here. Okay, so you guys can attempt this question. So 1, 2, 3, 4. Okay. So we know that temperature T1 is 300 Kelvin. Ratio R is 6. So we can calculate T2. T2 is already we have calculated in the last example. So T2 is 500 K. Then we have T3. T3 is equal to 1200 K, and we can calculate T4. T4 can also be calculated from relation T3 by T4 is equal to T2 by T1, which is equal to 500 divided by 300. So T4 can be written as 1200 divided by 5 by 3. So this will come out to be 720 Kelvin. Okay. So T2 will come out to be 720 Kelvin. So you can calculate what is the work of compressor and work of turbine. Work of compressor, we have already seen it is 200 CP, and CP he has given you 1.0 kilojoule per kg. So the work will be 200 kilojoule per kg. Okay. And you have work of turbine. Work of turbine, that will be equal to 1200 minus 720 into CP. That is 480 CP, and it will be equal to 480 kilojoule per kg. Okay. So work of turbine is 480, work of compressor is 200. So you can calculate W net. So W net will be equal to 480 minus 200, that is 280 kilojoule per kg. So W net developed by the engine or developed by the turbine is 280 kilojoule per kg. So now he is asking what is the mass flow rate. So to calculate the mass flow rate, we know that power is nothing but mass flow rate multiplied by W net. The power developed by turbine is mass flow rate multiplied by W net. So from here it is given that 1400 kilowatt is equal to m dot multiplied by 280 kilojoule per kg. So from here we can calculate mass flow rate, that is 1400 divided by 280, that is 5 kg per second. So the mass flow rate of the turbine or of the gas turbine which develops 1400 kilowatt of energy using the Brayton cycle is 5 kg per second. Is it clear? Okay. So I hope guys you have got certain idea of how does a gas turbine actually look like. I am sure you guys might have understood the simple Brayton cycle. There are different modifications of this Brayton cycle. So the first modification is reheating. Okay, that we will study when we will be studying the complete course. There are different modifications. There is a regeneration cycle also, which has come from Ericsson 1 cycle. So the Ericsson 2 cycle, which has been developed by Ericsson, was modification of Ericsson 1 cycle. So in Ericsson 1 cycle, the process is same like what we see over here, but that uses a regeneration, and there the heat transfer was happening at constant temperature also. So we will study that as well. But I'm sure you guys might have got a complete idea on how does a Brayton cycle actually looks like. So now if we go back to the Brayton cycle and then we see how does the processes look like. So I hope everybody will be able to understand. So the process 1 to 2, isentropic compression happening in compressor. 2 to 3 is the heat transfer happening at constant pressure. 3 to 4 is the work that is developed or in the turbine undergoing a process PV to the power gamma equal to constant, that is again isentropic expansion. And process 4 to 1 is heat rejection happening in heat exchanger. Okay, that leads to the efficiency of cycle as 1 minus 1 over r to the power gamma minus 1 divided by gamma, or it can also be written as 1 minus T1 by T2. Okay, so with this, let's stop it over here. I'm sure you guys might have understood and you guys might have thoroughly enjoyed. So guys, the lecture which we are going to teach you all in this series would be very conceptual, highly conceptual. We will be teaching everything from the basics. Even if you have studied or you have not studied, no matter, we will teach you everything. Okay, so this is the class of propulsion, which is basically the applications of thermodynamics. So this subject would be covered after the basic thermodynamics is covered, where we will study all the different processes which happens in thermodynamics. So there are 4 processes: constant pressure process, constant volume process, isothermal process, and isentropic process. So all these processes we will study one by one, and then we will go ahead and understand the cycles. Okay, so let's stop it over here, and let's meet in another class where we will discuss something else. Okay, thank you.